Hey guys, today we're going to learn about related rates. Now, related rate involves finding a rate at which a quantity is changing, and we do that by relating it to quantities that are of other rates who are already known. The rate of change is usually, and if not always, with respect to time, and we're finding the rate of change involves implicitly deriving known formulas. All of these formulas, when we find the derivative of any variable, since it's with respect to time, these would be all considered implicit functions. So for example, for the next two slides, we're going to go through most commonly used equations in these problems, and we're going to find their derivatives implicitly and write down what each rate represents. So this first equation is the surface area of a sphere. A is equal to 4 pi r squared. If I were to find the derivative, it would be dA dt. So that's the derivative of area with respect to time is equal to 8 pi r. And then because my variable is r, we multiply that with the implicit notation dr dt. So dA dt represents the rate at which the area is changing, and dr dt represents the rate at which the radius is changing. For volume of a sphere, that's V equals 4 over 3 pi r cubed. So when we find the derivative of this, the derivative of V would be 1, but you multiply by dV dt is equal to the 3 gets multiplied, canceling out the 3 of the denominator. So 4 pi r squared, and we multiply dr dt. So the dV dt represents the rate at which volume is changing. The next equation represents the Pythagorean theorem, but solved for a leg. So A is equal to the square root of c squared minus b squared, where c is a constant, so it does not represent a variable, so we don't have to find the derivative of c with respect to time since it's just a number. So we can write A as c squared minus b squared raised to the 1/2. So that means that dA dt is equal to 1/2 c squared minus b squared to the negative 1/2 times negative 2b dB dt. The 1/2 and the 2 would cancel, and so we end up with dA dt is equal to, the only thing left in the numerator would be the negative b dB dt over the square root of c squared minus b squared. Since this represents the Pythagorean theorem equation solved for A, dA dt is the rate at which the side is changing. And dB dt is the same thing, but for the other side, the rate at which side B is changing. So this is for side A and side B. Let's look at a couple more equations. We have the volume of a cylinder where R is a constant. So again, we don't have to worry about finding the derivative of R using the product rule because the radius does not change. So the volume of a cylinder derivative would be dV dt is equal to pi r squared, since this is just a number, and then dH dt. We've already figured out what dV dt is, but dH dt would be the rate at which the height is changing. Now here we have a triangle where theta is defined and you have side x over 15, and we're going, and you'll see we're not always just going to use cosine, we may use other trigonometric functions, but just so you get the idea of how to solve this, we have cosine theta is equal to x over 15. So if I were to find the derivative, it would be negative sine theta times d theta dt, because remember the derivative of the angle, is equal to 1 over 15 dx dt, where d theta dt is the rate at which the angle is changing. And we've already kind of established what dx dt would be in the previous slide for like dA, dt, and dB, dt. It represents the rate at which the side is changing. Now for the volume of a cone, now in the volume of a cylinder, just so you can understand why the radius is a constant, no matter where you go along the cylinder, the radius does not change. So we don't have to worry about r as being a variable. However, for a cone, depending on where you go along the cone, the radius does change. So we would treat the radius as a variable. And the height, even though the height of a cone obviously would stay the same, we also treat it as a variable because you're going to see that a related rate problem, usually heights will differ depending on the height of a water poured into a cone or coming out of a cone, or, you know, air filling up a balloon. You get me? Like height could change. So we're going to treat both r and h as variables, meaning that here we would have to use the product rule. So dv dt is going to equal, now I'm going to treat this as one function and this as another. So 2 over 3 pi r dr dt times h plus 1 over 3 pi r squared dh dt. And this would be my derivative. And you can always rewrite this if you like as 2 over 3 pi r h dr dt plus 1 over 3 pi r squared dh dt. Okay? Now let's look at how we would actually solve a related rates problem and what we do with these equations. So I put kind of like a general process that we can use for solving a related rates problem, and I'll walk you through that in a moment. So the first step is typically, if you want to, like if you're a visual person, you can draw a picture or a diagram to kind of represent your situation if you feel like you need that visual. You don't always need it, but just in case if you wanted to. Okay. 2, you would then find any equation relating all the information given. You're going to look to geometry for many of these formulas. You don't necessarily need to memorize a lot of these formulas. A lot of the time it is given to you in the AP exam, but it doesn't hurt to know them. Okay, and typically when we're trying to figure out what these equations, what equations we're going to need, we just write down everything that's given in the problem. Okay, then we're going to substitute in the formula any constants that we may have. So anything that is definitely not going to change, we can plug it into the formula before we differentiate. And remember that when we differentiate, we're always going to differentiate implicitly with respect to time. So everything will be over dt. Using all differentiation rules that apply, which would be, product rule, chain rule, quotient rule, whatever rule. Then we're going to plug in whatever information after. You only plug in constants before you differentiate. Then after you differentiate, you plug in all of the given information from the problem and solve for what you're trying to solve for. And always use complete sentences to answer the question that is asked. So let's look at this basic problem. Air is leaking out of an inflated balloon at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So before I even begin, I like to write down everything that's given. Since this is a rate and we are given cubic centimeters, anything that's cubed, that's volume. And additionally, this is rate, so that means that this is dV dt. Now, since air is leaking out, that means that the volume is going to be decreasing. So we would say that this rate is a negative 230 pi cubic centimeters per minute. Now, I like to always write my units so that way when I find my final answer, I know what units exactly to use. At the instant when the radius is 4 centimeters, so this is not a rate because it's not telling you per minute, that means that the radius is equal to 4 centimeters. What is the rate of change of the radius of the balloon? So we are looking for dr dt. So once you look at all of this given information, notice that if we're given the rate of change of volume, that means that I would need my volume equation, which is the volume of a sphere. And the volume of a sphere, because a balloon is a sphere, would be 4 over 3 pi r cubed. Now, the 4 centimeters is not a constant. Because this balloon is deflating, the radius is going to change all the time until, there's no more air. So we cannot plug in the 4 yet. Right now, we're going to just differentiate. So dV dt is going to equal to 4 pi r squared dr dt. Now we're going to plug in everything that we know. I know dV dt is negative 230 pi is going to equal to 4 pi. Now here, this is for my radius at the moment, which is 4 centimeters squared. And we need to solve for dr dt. So at this point, it should be pretty clear on how to solve. We don't really have to do much else. We can just simplify this. So negative 230 pi is equal to 4 squared, which is 16, and 16 times 4 is 64 pi dr dt. So to solve for dr dt, we're just going to divide the 64 pi. So we have that dr dt is equal to negative 230 divided by 64. And you can simplify this if you want. You can also, if this was a calculator question, this would equal to negative 3.5937. And don't forget your units. Since this is the rate of change of the radius, this is going to be centimeters, because that's my units for the radius, and over time, which is minutes. So what does this mean? This means that the rate at which the radius is decreasing is 3.5937 centimeters per minute. Let's look at another example. We're just going to look at tons of examples for this lesson because all of these questions there's not a set way of solving every single one. It's always going to be changing and it depends on the information that's given. So we need to know how to apply a general rule, like a general process for them, but not every question will be the same. So here we have that water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. So water is leaking, and this is a rate. So that means that the height of the water in the tank is decreasing by 3 cubic, 3 cubic feet, my bad. If you ever see cubic, that means volume. So this is dV dt. If the radius of the tank is 4 feet, at what rate is the height of the water changing? So we're looking for dH dt. So let's write down everything that we know. We know that dV dt is going to equal to negative 3 cubic feet per second, and it's negative because it is leaking. The radius is equal to 4, and we are looking for dH dt. Now, because we're given dV dt, that means that we must use the equation for volume, and the volume of a cylinder is pi r squared h. Now remember, in a cylinder, even if the water is leaking, let's say it's, the height is decreasing, the radius, no matter where you go along the cylinder, is always going to equal to 4. So that radius is considered a constant, and I can plug that in before I differentiate. So volume is equal to pi r squared, so 4 squared, 16 pi h. And now we can differentiate. So dV dt is equal to 16 pi times dH dt. We are given dV dt, which is -3, is equal to 16 pi dH dt. And to solve for dH dt, we would divide the 16 pi. Now, if this was a non-calculator question, you don't have to do anything else. Just leave it just like that. So dH dt is -3 over 16 pi, my units, which is feet per second. Now, I know that a lot of the times we're not sure how to write out our units. So just as a heads up, for volume, your units will always be cubed. So feet cubed per second, meters cubed per minute, whatever, cubed per unit of time. That would be your rate. If this represented area, like if I was trying to solve for dA dt, then your units would be squared. So feet squared per second, or a meter squared per minute, or etc. But if your unit is just one dimension, right? So either height, a radius, a side, I don't know, a length, anything like that, it would just be your unit per unit of time. So feet, meters, miles per second, per minute, etc. So no exponent. So that's how you can guide yourself on your units. Oh, and just if you had to write this out, this would be that the height is decreasing at a rate of 3 over 16 pi feet per second. Notice I didn't have to put -3 over 16 pi because I already said that it is decreasing, which implies that negative. Okay, let's look at this next one. A beach ball is inflating at a constant rate of 10 pi cubic centimeters per minute. When the volume of the ball is 256 over 3 pi cubic centimeters, what is the rate of change of the surface area? So I put here all of these formulas. So let's write down what's given. We have here this 10 pi cubic centimeters that is inflating. So that means that this ball is going to get bigger. So dV dt is a positive 10 pi cubic centimeters per second. Again, I know that this is volume because my unit of measurement is cubed. We are given the volume, which is equal to 256 over 3 pi. And we are looking for the rate of change of the surface area. So this is several equations, right? We are given the equations for the dV dt, but we're solving, or what we want to solve for is ds dt. So I have here both these equations. Because we're given volume, what we're going to have to do is use the volume equation. And you'll see that when we use the volume equation, the unknown that we would have is the radius, or the dr dt, etc., which we can solve for, which we need in order to find the ds dt because we have the radius in that equation. So we're going to start with volume. So volume is equal to 4 over 3 pi r cubed. Now, when I find the derivative, this would be dv dt is equal to 4 pi r squared dr dt. Now there's a problem, right? So I have dv dt, but I don't know the radius and I don't know the rate of change of the radius. So a lot of these related rates problems, there's really no set way of going about it. It's kind of just using your equations and trying to figure out a way of getting all of those unknowns. Because that's the problem with these related rates problems, is that we have a lot of unknowns. So since I need the radius and I'm given volume, what I can do here is I can plug in 256 pi for the volume here and solve for the radius. So let's go ahead and do that. So 256 over 3 pi is going to equal to 4 over 3 pi r to the third. In order to solve for r to the third, what I could do here is multiply by 3 over 4 pi. That way it would cancel out the pi's and it would cancel out my fraction and we would have r cubed by itself. So I'm going to have to multiply it here, 3 over 4 pi. The pi's would also cancel and the 3's would also cancel. And we have 256 divided by 4, which would equal to my radius cubed. Now 256 divided by 4 is 64. So if I cube root both sides, I get that the radius is equal to 4. So now that I have that piece of information, what I could do is I could plug it in here into my dv dt equation. And since I have dv dt, I can plug that in as well. And then I can solve for dr dt. So dv dt is 10 pi is equal to 4 pi times 4 squared dr dt. 4 squared is 16, and 16 times 4 is 64. So 10 pi is equal to 64 pi dr dt. So now to solve for dr dt, we're just going to divide by 64 pi. And here my pi's would cancel. And 10 over 64 is divisible by 2, which gives us 5 over 32. And this is dr dt. So I'm just going to circle these just so that I know where I'm at. Now, the reason why we're going through all this is because if we start now trying to figure out what ds dt is, which is the end goal here, right? My surface area, S, is equal to 4 pi r squared. So when I find the derivative, that's ds dt would equal to 8 pi r dr dt. If you would have done this at the very, very beginning, that's fine. But then you would have noticed that you have all of these unknowns. You have the missing radius and the missing rate of change for the radius. So then you would have had to go back and use the volume equation and the dv dt equation. So regardless of how you figure it out is fine, but you are going to have to kind of, problem solve. But I have my radius and I have the dr dt, so I can plug everything in. So ds dt is going to equal to 8 pi times the radius, which is 4, times dr dt, which is 5 over 32. Now 8 times 4 is 32, so that's going to cancel with my 32. So ds dt is equal to 5 pi, and now we have to look at my units. This is area, so this would be square centimeters or centimeters squared per second. Let's look at what I call the dreaded cone problem. So cones typically give most people a hard time. So we're going to take our time with this one. Okay, it says a cone has a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone, so the height of the water level is changing at a rate of 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, at what rate is the volume of the water changing? So there's a lot of information here that we have to break down. All right, I'm going to draw a visual here so you understand. Here's my cone. We are told that the diameter is 10 inches, but we never use the diameter. We only use the radius. So that means that the radius is equal to 5 and the height is 15. Now, no matter where you go on the cone, if water is being poured into the cone, both the radius and the height are always changing. So R and H are both variables. That means that when you differentiate V, we would have to use the product rule. But we're going to avoid that because we have two, if we use both R and H as variables, then we have too many unknowns. But let's keep writing down what else is given in this problem. It says that the water level is changing at a rate of 1.2 inches per second. This is the height. So we are given dH dt, which is equal to 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, so the radius is 2, at what rate is the volume of the water changing? So we're looking for dV dt. Now, whenever we have a cone problem, and I wrote it here, most cone problems will require you to write a ratio of the height to the radius so that you can rewrite the equation of the volume of the cone in terms of one variable rather than two. So that means that because I'm given dH dt, I'm going to write a ratio that relates the radius with the height so that I can replace the radius with an expression in terms of h. So this is what I mean. For the entire cone, when the radius is 5, the height is 15. So the ratio for the radius to the height is 1/3. Now I want an expression with just h, meaning I'm going to solve for the radius. So if you're looking for, if you want to write your equation for volume in terms of h, you solve for r. If you want to write the equation for volume in terms of r, you solve for h. So here I want it with h since I'm given dH dt. Because if I used r, then I would need dr dt. So I'm going to multiply h to both sides. So the radius is equal to 1/3 h. So now what I can do is I take my volume equation and instead of using the radius squared, I'm going to use this, the 1/3 h, and then I'll square that instead. So now I'm going to rewrite this equation by simplifying this a bit. Volume is equal to, now here 1/3 h squared, that's 1/9 h squared. 1/9 times 1/3 is 1/27 pi, and then h squared times h is h to the third. Once I have it written like this, now we can differentiate and all we would have is dV dt and dH dt, which is what I have here. So let's differentiate. We have dV dt is equal to, now 3/27 would be simplified to 1/9 pi h squared dH dt. Now here we run into one more problem. We have dH dt, but we don't have the height, and I'm trying to solve for dV dt. But we are given the radius. So what I can do here is I can take the radius and I can figure out the height because I know that the radius which is 2, is going to equal to 1/3 of the height. So now I can just solve for h by multiplying the 3. So h is equal to 6 at the moment that the radius is 2. So now that I have everything I need, I can plug everything in. So dv dt is equal to 1/9 pi times 6 squared times 1.2, which is the dh dt. And if I multiply everything together, this is 1/9 pi times 36 times 1.2. And I'm just going to save some time. I had already multiplied everything with the calculator. 1/9 times 36 times 1.2 is 4.8 pi. And because this is dv dt, this is inches cubed per second. So the volume of my cone is increasing at a rate of 4.8 pi inches cubed per second. Let's look at another example of a cone problem. An inverted cone is 20 centimeters tall and has an opening radius of 8 centimeters. So this is what that would look like. Here's my cone. This is 8 for my radius, and the height is 20 centimeters. And was initially full of water. The water now drains from the cone at a constant rate of 15 cubic centimeters each second. So that is dv dt. And it would be negative 15 because the water is draining. So negative 15 cubic centimeters per second. The water's surface level falls as a result. At what rate is the water level falling when the water is halfway down the cone? So we are looking for dh dt, the water level, when the water is halfway down the cone. So if the height is originally 20, that means that the height is going to be 10 centimeters. So now remember, for this, we have the two variables, r squared and h. Since we're looking for dh dt, we want this equation to be only written in terms of h. So I'm going to write my ratio. So r over h is going to equal to 8/20, which can be simplified to 2/5. So now I want my equation to have h in it, so that means that I need to solve for the radius. So I'm going to multiply h to both sides. So the radius is equal to 2/5 of the height. So now I can go back to my volume equation. So volume is 1/3 pi times the radius, which is 2/5h times h. And this is squared, sorry. Let's simplify this before we find the derivative. So v is equal to 1/3 pi times 4/25 h squared times h. Putting everything together, this gives me that the volume is equal to 1/3. Sorry, the whole point was to simplify. So I can multiply this 1/3 with the 4/25, which would give me 4/75 pi h to the third. And now we can find the derivative. So dv dt is equal to, now when I multiply 3 and 75 can be simplified. So that would be 4/25 pi h squared dh dt. Now in this particular case, you don't need to solve for h because we are given that h is 10 centimeters. So now we just plug everything in. So negative 15 for my dv dt is equal to 4 over 25 pi times 10 squared dh dt. Let's work on simplifying this a little bit. This is negative 15 is equal to 4 over 25 pi times 100 dh dt. Now 100 divided by 25, because remember whatever's in the denominator is being divided, I can simplify that to be 4. So we get negative 15 is equal to 16 pi dh dt. So now to solve for dh dt, we would just divide the 16 pi. So dh dt is equal to negative 15 over 16 pi, and this is centimeters per second. Let's look at what an FRQ would look like for a related rates problem. We have here that a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So first I'm going to draw this out just so you can see what's going on. Here's the wall and here's the ladder. And the ladder is being pulled away from the wall. So we have here a right triangle. We have that the ladder is 25 feet. We're going to call this X and this Y, since these are both unknowns, because as the as the ladder is being pulled away from the wall, dx dt is going to increase, while dy dt is going to decrease, because the ladder will be going down the wall but away from the wall. So we're given that dx dt is equal to 2 feet per second. And it's positive because, again, if the base of, this is the base of my ladder, if it's being pulled away, the distance between the base of the ladder and the wall is going to increase. So that is a positive number. And then for part A, it says how fast is the top of the ladder moving down the wall. So we're looking for when this is going down, when the base of the ladder is 7 feet from the wall. So we're trying to find dy dt when the when the x value is 7 feet. And it's the x because it's when the base of the ladder, this is the base of the ladder, is 7 feet from the wall. So whenever you have a right triangle, what you're going to have to use here is the Pythagorean theorem. So the Pythagorean theorem, as we know, in this particular case is going to be x squared plus y squared is equal to the hypotenuse squared, which is 25. If I find my derivative, we get 2x dx dt plus 2y dy dt is equal to 0. Now the problem here is that we're trying to find for dy dt, we have x and we have dx dt, but we need the y. So in order to solve for y, I can use my original Pythagorean theorem and plug in my value for x, since I am given that the x is 7. So 7 squared plus y squared is equal to 25 squared. 7 squared is 49. Plus y squared is equal to 625. When you subtract the 49, you get that y squared is equal to 576. And when we square root, we get that y is equal to 24. So now that we have my y, we can plug in the y, the x, the dx dt, and then solve for dy dt. So 2x, which is 7, dx dt, which is 2, plus 2 times y, which is 24, times dy dt is equal to 0. 2 times 7 is 14, times 2 is 28, plus 2 times 24 is 48, dy dt is equal to 0. Subtract the 28, we get that 48 dy dt is equal to negative 28, and then divide the 48. So we get that dy dt is equal to negative 7 over 12, because I can simplify this by 4 feet per second. And remember that we said dy dt should be negative because it is moving down the wall. So that height would be decreasing. So it makes sense that we end up with a negative answer. For part B, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So remember that the area of any triangle is 1/2 the base times the height, which in this case we're using x and y. These are both variables, and here I don't have to solve for any of the others because we have dy dt, which we just solved for. We have dx dt, we have y, we have x, we have everything we need. So we can just find the derivative by using the product rule, because x and y would be a product. So dA dt is going to equal to 1/2 y dx dt plus 1/2 x dy dt. Again, I have all of these values because it's when the base of the ladder is 7 feet from the wall. And when it was 7 feet, which was the same as in part A, we already solved for y, which was the 24. And we have the dy dt. So we just plug everything in. So 1/2 times y, which is 24, times dx dt, which is 2, plus 1/2 x, which is 7, times negative 7 over 12. And now we can simplify this. Half of 24 is 12. 12 times 2 is 24. Oh, I guess I could have just canceled this. And then this would be minus half of 7 times negative 7 over 2 would be negative 49, right? 7 times 7 over 24. We can rewrite this, right, using common denominator. So I would have to put this over 24 and then multiply this by 24, which would equal to 576 over 24 minus 49 over 24. And 576 minus 49 is 527 over 24. And this is, since this is represents dA dt, this would be feet squared per second. Since it is area, your units have to be squared. Moving on to part C. Find the rate at which the angle formed by the ladder and the wall of the house is changing when the base of the ladder is 9 feet from the wall. So we're going to draw this triangle again, just so you can get an idea. This is the ladder, and this is the wall. So they're talking about this angle here. Now remember that the base of the ladder here, or rather the base from the ladder to the wall, so the base of your triangle is always changing. So I'm labeling that as x, and we're using this because it's saying that we want to know the angle when the base of the ladder is 9 feet from the wall. So we want to know when x is equal to 9. And the ladder, no matter what, does not change, so this is still 25. So because we're looking for the rate at which the angle is changing, okay, we need to use trigonometry. Anytime that you're trying to solve for an angle or the rate of change of an angle, we have to use sine, cosine, or tangent. Now, because this is the opposite and the hypotenuse, that means that we are going to use sine. So we're going to create an equation that uses sine of theta, which is equal to the opposite over the hypotenuse. And now we're going to differentiate. So sine of theta is cosine theta times d theta dt is going to equal to 1 over 25 dx dt. Now the cosine of theta, we don't know the angle, right? And we don't need to know the angle. I can find the cosine of theta if I solve for the missing side, and then remember SOHCAHTOA, right? I'll write it down here just in case. Cosine is the adjacent over the hypotenuse. So if I know my adjacent side, then I can just put that over 25, and that would represent the cosine. So I'm going to use my x is equal to 9 and that the hypotenuse is 25, and I'm going to solve for y. So 9 squared plus y squared is equal to 25 squared. 9 squared is 81 plus y squared is equal to 625. And when we subtract, we get y squared is equal to 544. And then when we square root, we get that y is equal to the square root of 544. So if we could simplify this radical, we would, but there's no square root of 544, so we're just going to leave that. So now let's go back to this equation. We have the cosine of theta, which is equal to adjacent, so the square root of 544 over the hypotenuse, which is 25, d theta dt is going to equal to 1 over 25 times dx dt. And dx dt was given in my problem, and which we've been using as 2. So we're going to multiply this with 2. And now to solve for d theta dt, we would multiply by the reciprocal of that fraction. So d theta dt is going to equal to 2 over 25, which is what I have here, times the reciprocal of this, which is 25 over the square root of 544. The 25's cancel, so d theta dt is going to equal to 2 over the square root of 544. And if you're ever solving for the rate of change of an angle, the unit will always be radians, because we only use radians here in calculus. So radians per unit of time, which was given to be seconds. Okay, let's look at another example. I told you we would be doing lots of examples. And this one is another type, like a part of an FRQ. These two are completely separate, but these are typical type questions. So this first one, an airplane is flying at an altitude of 5 miles and passes directly over a radar antenna. When the plane is 10 miles past the antenna, the rate at which the distance between the antenna and the plane is changing is 240 miles per hour. What is the speed of the plane? Now, whenever you see this, the speed of something in terms of related rates, this is the rate at which the distance of the plane is changing. So I'm going to draw a diagram here to kind of give you a visual. I'm going to call this my airplane. And this is the radar antenna, because remember it starts right above, and it's at an altitude of 5 miles. When the plane is 10 miles past the antenna, so right here, this will represent x, because of course the plane is always moving, then this distance is going to obviously change as well. So we'll call this y. When the plane is 10 miles past the antenna, so at the moment when x is equal to 10, the rate at which the distance between the antenna and the plane, so here's the antenna, and the plane is now here. So dy dt is equal to 240 miles per hour. And it's positive because the distance is going to be increasing. So what is the speed of the plane? The plane goes along here, what I have labeled as x. So the speed of the plane would be represented by dx dt. So I am trying to solve for dx dt. So again, I have a right triangle here. So we're going to use the Pythagorean theorem. So x squared plus the 5 does not change because the plane is just going horizontally. It is not going up or down. So this is a constant. So we'll say 5 squared is equal to y squared. When I find the derivative, we get 2x dx dt, which is what I'm trying to solve for, plus, well, not plus anything, it would just be 0, right? Because 5 squared is 25, and the derivative of that is 0, 2y, and then dy dt. Now I have dy dt, but I don't have y. And just like in the other triangle problem, we can use this Pythagorean theorem to solve for y. We were given that when x is 10, so 10 squared plus 5 squared is going to equal to y squared. 10 squared is 100 plus 25, so 125 is equal to y squared. And when we square root both sides, y is equal to the square root of 125, which you can simplify that radical, and it would be helpful if you do, to 5 square root of 5. So now, and if you need a reminder of how to simplify square roots, 125 is 25 and 5, and then 25 is 5 and 5. So this 5 gets to go on the outside, and this 5 would have to stay on the inside. So that's where that came from. So now that we have the y, we can go ahead and plug everything into my equation and solve for dx dt. So 2 times x, which is 10, because I'm going off of this, times dx dt is equal to 2y, which is 5 square root 5, dy dt, which is 240. And now we can solve for dx dt by dividing this 20. So dx dt is equal. Now I can simplify even just like this, so I can get rid of this 20. 24 divided by 2 here is 12. So what I have to multiply here is 12 times 5 times 2. So dx dt is going to equal to 120, because 2 times 5 is 10, 10 times 12 is 120, square root 5, and then remember proper units, this is miles per hour. Last question here. The radius of a sphere is increasing at a rate of 2 inches per minute. Find the rate of change of the surface area of the sphere when the radius is 6 inches. And as a reminder, the surface area of a sphere is 4 pi r squared. So let's write down everything that we have. We have the radius is increasing at a rate of 2 inches per minute. So that is dr dt will be a positive 2 inches per minute. We are looking for dA dt when the radius is equal to 6. Now this is a more clear-cut problem, and you'll see that some related rates problems would be pretty simple to solve as long as you can identify all of the given information and use the proper equations. And then some would be like the cone problems or the ones with the Pythagorean theorem where you have to do a lot more work. So not all related rates problems are approached in the same way. So we're going to take this equation here and find the derivative, which would be dA dt is equal to 8 pi r dr dt. And in this one, we don't have to really do much else because we have the dr dt and we have the r. So we can just plug everything in and solve. dA dt is going to equal to 8 pi times 6 times 2, which would give me a final answer of 96 pi inches, now this is area, so squared, per minute. All right, we're almost near the end. We have one more. A spherical balloon is expanding at a rate of 60 pi cubic inches per minute. So I'm just going to write this down. That's dV dt because of the cubic inches, which is 60 pi per second. How fast is the surface area of the balloon expanding? So we're looking for dA dt. When the radius of the balloon is 4 inches. All right, so obviously since we're looking for dA dt, we're also going to need the equation for the area of a balloon, the surface area of a balloon, which is, as we saw before, 4 pi r squared. If I were to just start from here, right, because this is my end goal, is to find dA dt. If you do that, you would get dA dt is equal to 8 pi r dr dt. Now I have the radius, but I don't have the dr dt. So that's a problem. But I notice in my given information, I'm given dV dt. So that's kind of a clue as to I may have to use the equation for volume in order to solve for dr dt. So we're going to get our equation for volume and plug everything in, or rather differentiate. So dV dt is going to equal to 4 pi r squared dr dt. See, and now I'm given dV dt and I'm given the radius, so dr dt would be my only unknown, which I can use this equation to solve and then go back and plug it in. So dV dt is 60 pi is equal to 4 pi times the radius, which is 4 squared, so 16 dr dt. 4 pi times 16 is 64 pi. And that's going to equal to the 60 pi. So to solve for the dr dt, we're just going to divide by 64 pi. And we get dr dt is equal to, these pi's would cancel, and 60 over 64, both of these can be divided by 4, which gives me 15 over 16 inches per second. So I have dr dt. I'm ready to go back here and plug it in. So dA dt, which is my final goal, is equal to 8 pi times my radius, which is 4, times 15 over 16, which is the dr dt. And what I like to do here is I like to simplify as much as I can before I even multiply. 8 and 16 can be divided by 8. And then 4 divided by 2 is 2. So really dA dt is just when I multiply the 2 pi with the 15. So 30 pi, and this is, remember our units, inches squared per second. Anytime that you solve for any rate or anything at all, always, even if it's not your final answer, like I did here, I still wrote inches per second. Always write your units because you never know if they're going to be looking for that. I know this was lengthy, but I appreciate you getting through the whole thing. So that's it. Those are related rates.